Today, I want to give a little bit of an introduction to Arduino and its applications in music. I want to help you to start thinking about what role these Arduinos might play in your production of electronic sound, either through voltage or digitally. Arduino and Arduino-type devices are all microcontrollers, basically very simple computers. We program them with software to react to different inputs and give different outputs. For example, as I showed in my MIDI-controlled glitch Genesis, the Arduino takes in MIDI messages and then outputs voltages that create the visual glitches. In my short piece Coffee Time, an Arduino gets data from a pressure sensor and a thermistor, a temperature-dependent resistor, and sends that information to the computer to control the digital sound in real time. So for electronic musicians, Arduino can be particularly useful in designing custom interfaces, building an interface from the sensors you need, so you no longer need to use pre-existing devices, MIDI keyboards, MIDI controllers, or even joysticks. You can create your own controllers, limited only by your imagination and technical skills. I recently picked up the third edition of Handmade Electronic Sound by Nicholas Collins, and was happy to find that there's a chapter about microcontrollers and Arduino by Joseph Kramer. In this chapter, Kramer uses the Arduino to generate tones like an oscillator, which is not something that I'd done before. Instead, I'd used Arduino as a control for computer-generated sounds. But I think this is a great demonstration of voltage becoming audio. I don't intend this video to be a replacement for the text in any way, and Kramer takes this project in a different direction than I do. I dug through my drawers a bit here and found a very old Arduino Uno. This says that it's revision 3. This was the Arduino that I started working on, 7 years ago, so I don't know if this is a collector's item or not now. Here's our microcontroller, very, very big, but we can see other things here, a clock, LEDs, and so these are the other parts that are on the board. This, I don't know if it's Arduino brand or if it's an Arduino compatible microcontroller. This says Arduino Pro Mini on it. These are nice small ones that they have a lower profile. Maybe not as great for doing prototyping. There's not as many bells and whistles as these big boards, but once you know what you're doing and what you need, they might be a good choice. Next, that's similar in size. This is a Teensy. This is what I used in the Sega Genesis glitch band, as well as the IntelliVoice synthesizer, where I use the Arduino to trigger the IntelliVoice synth. Today I'm going to be using this Adafruit Metro. I like these. I think Adafruit's a good company and they have good products that are generally a little bit cheaper. This is 2020, I'm recording this. I think this Arduino Metro is $16 as opposed to the Arduinos, which I think run $22. If you're buying a whole stack of them, then it starts to add up. Set these aside for the moment. Let's look at the Metro. The Metro is going to be connected to my computer through this USB cable. And that's how we're going to program it, and it's also how I'm going to power it. This is too small to see, maybe I'll post a close-up, but you can see that we can send 5 volts out, 3.3 volts out, so we're not going to need any kind of external battery. We're going to power this through the computer. Now, another project in the Nicholas Collins book, an easy oscillator that you can make is this here. This is a hex Schmidt trigger. I think he calls it my first oscillator. I'm not going to do any kind of walkthrough on how to make this. I will link, however, Nicholas Collins' walkthrough on how to make it, which is really superb. Basically, I just have this one chip, this 40106 chip, that I'm powering with a 9-volt battery. This chip has a bunch of inputs and outputs on it. It takes what it gets at the input and reverses it. So for example, if it gets a voltage on the input, it sends no voltage. If it gets no voltage, it sends a voltage. So we can turn this into an oscillator by feeding it back on itself. To use a metaphor, think about someone standing by a light switch and you tell that person, okay, if the lights are on, turn them off. If the lights are off, turn them on. If the person follows those rules, the lights are going to flick on and off super fast. Well, I mean, as fast as they can flick that switch. Because as soon as they're on, their rule is to turn them off. As soon as they're off, their rule is to turn them on. So this circuit is neat because it just requires a few components, this chip, a capacitor, and a potentiometer, and then we can hook up a battery, and I just have my piezo here for output. Negative, positive, and I know that's quiet. Let me use this box as a resonator here. And then I can adjust the resistance. Okay, so we have an analog controlled oscillator. Again, it's just flicking on and off. If we do that between 20 and 20,000 times a second, which is the range of human hearing, we're going to get a sound. Okay. Again, I encourage you to check out Colin's book and or his YouTube video, which I'll link in the description if you're interested in learning more about that. So what we'll do is we'll use our Arduino. So I'm going to take that piezo, and then let's think about how this wants to go. Now, this was vibrating because we were sending that voltage on and off. Again, flicking that light switch on and off, we were sending the voltage and then turning it off and sending it and turning it off between 20 and 20,000 times a second. I could do the same thing with the Arduino. But this is being powered by the board, and I can just program the microcontroller to turn this on and off. Let's start very, very simply. So I'm going to take this, and I'm going to look down the sides here. I'm going to plug in the black wire into the ground. And then right next to it, there's 13. This is a digital pin. This is number 13. Let me plug the red wire into there. Now, I can power up this board, but nothing's going to happen. And the reason for that is oops, I've made a mistake. This is my Arduino. I wanted to use the Adafruit today. Where'd that go? So, in order to program this, I need to connect the USB cable, and then I'm going to hop over to my computer and open up Arduino on my computer, and we'll write the program that will oscillate this piezo. So let's hop over to that. Okay, so here I am in Arduino, and this is the program that I'm going to upload to that microcontroller, how I'm going to program that microcontroller. There are two main parts to Arduino programs: the setup and the loop. Arduino programs are called sketches. What happens when we upload this sketch to the Arduino is first, when it turns on, it runs the setup one time. And then after it runs the setup one time, it keeps going through the loop again and again. So let's add some code here. The first thing we want to do is we want to tell Arduino which pin we want to send that voltage to. Remember, we're going to use voltage switching on and off to vibrate our piezo. So I'm going to say int for integer, and then I'm going to choose a name for that pin. I'm going to call it audio pin. And if you remember, I plugged the piezo into 13. So there we go. So now all I've done is I've named pin number 13 audio pin. We need to tell Arduino that we want to write to that pin. As I said before, Arduinos take input and output. We can use these pins as control, but we want to tell the Arduino that no, we're not reading what's coming into this pin. We want to send voltage out. So I'm going to write pin mode with a capital M, camel case. This is a command for Arduino. And then I want to tell it that my audio pin, which is 13, will be all capital output, close parentheses, semicolon at the end of the line, and make sure that we've got the semicolon at the end of each line. Okay? I'm going to put these two slashes. This is a comment. This is a note to me. Arduino doesn't run the things that are behind slashes, but it helps me remember. So designate pin as output. So now it's run that once, it's set that to be an output, but now we need to tell it to turn that pin on and off. And again, we need to do it between 20 and 20,000 times a second. So we'll do what's called a digital capital W write. Where do we want to write? We want to write to that audio pin with a capital P. And then we want to write high. So that tells it the voltage should be up. End of the line, semicolon. And then what we're going to want to do after that is we're going to digital write audio pin low, right? Because we want it to flick on and off. This is what we need to do. Again, voltage goes up, voltage goes down, and then we get the vibration. The problem here is I have no idea how fast that vibration would go. It would keep running through that program and going through those steps, and we might not actually hear anything. So let's do it this way. Let's add, oops, not a delay, a delay. The unit here is milliseconds, so 5 millisecond delay there. Copy, paste, and then a 5 millisecond delay, and again, semicolon at the end. So what'll happen is it'll go up for 5 milliseconds, down for 5 milliseconds. So what that means is we've got a period length of 10 milliseconds, right? Up for 5, down for 5, that's 10. How many hertz is that? Well, how many times does 10 milliseconds happen in a second? I paused for dramatic effect there, but the answer is 100. So this should be 100 hertz, right? The way I figured that out is I took 1,000 milliseconds and I divided it by 10 milliseconds, right? Because 1,000 milliseconds in a second, and we have a cycle of 10 milliseconds. Okay, let me go up here and click on the check mark. Oops, it wants me to save it first. That's fine. Let's call it oscillate. Save. And now it's gone through it. It says, hey, this is A-OK and ready to upload. You actually could just upload it without verifying it and it'll give you the mistakes before it compiles it, but my habit is to always click on verify. I'm going to go up here, and now what's important is I have the Arduino plugged in, and I also have it selected as the outgoing port here. I believe for this Adafruit Metro, I had to install some additional software, but basically I just followed the steps that were on the Adafruit site. So I needed to install something to allow me to run Arduino on this, not Arduino, but Arduino compatible board. So that's all set. Let me upload now. Oops. Okay, I don't know what caused that problem right there. My solution was I unplugged my Arduino and I plugged it back in. So again, as with everything in life, restarting the program, unplugging it and plugging it back in, it solves most of your problems. All right, let's have a listen. So whoops. So I don't have absolute pitch, so I can't tell you if that's 100 hertz. What I will do in the edit of this video is I'll cut in something at 100 hertz. I'll generate 100 hertz in Audition or something, and we can see if this is accurate. I'm going to unplug that so it stops making the tone. Now, if it's not accurate, there might be a couple of reasons for this. One is that the Arduino might not be able to precisely keep up with this. So I'm a little bit dubious, honestly, about Arduino's ability to keep up and make accurate pitches, which is why I haven't used it as an oscillator before. Now, that's probably not a big deal. Again, we're making chip tunes here. We're making Arduino chip tunes. So accuracy probably isn't our primary aesthetic concern. So what I'd like to do now is let's control the pitch of this oscillator using a potentiometer. So let me bring this over, and we're going to make something a little bit more sophisticated. I'm going to take the potentiometer I had on that Schmidt trigger, and I'm going to put it over here. And now let's send this potentiometer a voltage. So I'm just, for now, going to take a wire from here, and I'm going to send this from the 5 volts that come off of the board. Again, so this power will be coming through the computer, but it'll be coming through the Arduino, and I'm going to run power to this potentiometer. On the other outside pin of this potentiometer, I'm going to ground that, So again, outside, it doesn't matter which side, but one outside pin is the voltage, one outside is ground. And then the last thing I'm going to do, I'll try to find a different color wire here. Here's a green. Oh, that's a blue one. No, I used blue before. Here's a green one. Thought I had a yellow one somewhere. But anyway, I'll run from the middle. And now I'm going to run this to a place that the Arduino can read it. I'm going to run this to A0. So you'll notice the inputs on this side of the Arduino have A's next to them. This means analog. So we were using a digital pin. Remember, we were digital writing something on and off. And so digital means it's 1 or it's 0, it's on or it's off. The analog is going to be able to have a continuous stream of values. So let's hop back over to our code here and write a way to read this. That analog pin is going to read from 0 to 1023. So let's start though by just going int pot pin equals, and I'm just going to put A0. That's where we're going to be reading from. And so now let's set up a new variable, int, again, integer, delay time, and let's set that to be, well, I guess we don't need to set that to be anything. Again, always ending with a semicolon there. And so now, before I write to this digital write, let me put in delay time to equal analog read from the pot pin. So now our delay time is going to read the value of that potentiometer and change the delay time, well, which we need to now change here, paste, to be somewhere between 0 and 1024. All right, I'm plugging my Arduino back in. It immediately makes a sound because it's got that old program still on it. But let's verify this program. It seems to like it. Make sure the right board is selected in our port, and let's upload it. It starts out clicking very slowly. Now let's think about that. If our delay time is 1000, that means that we're at 0.5 hertz, which is way below the threshold of human hearing, so we won't hear that. Okay, so I would say this is working, but it's not great. The range of numbers we have coming in isn't an effective range of numbers for us to set the delay time at without some transformation. I could do something like delay time equals analog read pot pin times 0.5. We can plug this in and see if this makes it better. Verify. So now it only goes up to 512. Let me even go 0.25 and see if that improves things. Now we'll upload it. Okay, that's not bad. We could make this stepped, though, too. Let's think about that. I'm going to add another variable here called pot read. And so I'm going to change just reading the delay time. I'm going to read it once into this variable pot read. And let's set that back to the 0 to 1023. So then I can take this and say, well, if the pot read is less than 200, then what should we do? If that's the case, then we'll set our delay time to be 2 milliseconds. Otherwise, delay time equals 10 milliseconds. Verify. Plug it in. Upload it. Okay, so now I got this playing 2 different notes. Again, I just can't have that tone going all the time. I should have put in a button. All right, what if we went else if the pot read is less than 400? Okay, so if it's less than 200, the delay time is 2. Otherwise, if it's less than 400, make it 10. Otherwise, if it's not of, pot read is less than 600, and I'm just gonna copy this, then we do 800. Okay, so then we'll do delay time equals, I'm just picking random numbers. I'm not thinking about frequencies here. I'm just sort of coming up with different numbers. I'm keeping them very low because I want it to be in the audible range. Delay time equals, let's just do 17. And then last, else, so if it's greater than 800, delay time equals 20. Save, verify. Oh, I've made a mistake. Else if pot, oh, I misspelled pot read. Boom. Verify. Made another mistake because I did it again because I copied and pasted. Verify. Looking good. Oh, and now I didn't plug in the board. I'm plugging it in. There's that sound that lets me know it's plugged in. Upload it. That jumped from 2 to 10 is too much. So let's do 2, 5, 7, 10, and then 15. And let's see how that does. I still feel that jump from 2 to 5 is big. Let's go 2, 3, 4, 6, 9. Hey, and so now I've got something that steps through 5 different notes. So this is cool. This would be very difficult to accomplish with just electronic components using that hex Schmidt trigger. But with the Arduino, I can program it to react to those different resistances as I turn the knob and output different frequencies. Now, there are tons of ways to expand on this. Think about light-dependent resistors. Think about different ways you can read from that analog read. And of course, buttons to control things. You could count the number of times you push a button and change pitches based on that. You could run different buttons into different pins and look for voltages across that and make essentially a piano keyboard. And remember, you don't have to use Arduino as the sound source itself. You can use it to pass data to your computer or other devices as control information. We'll save those conversations for another day, though. Good luck. Let me know what you come up with.